In this chapter, we're going to look at AC, or alternating current circuits. AC, which stands for alternating current circuits. In a previous chapter, we dealt with DC circuits, where the voltage or the current is constant in time. AC circuits are circuits where the voltage or the current vary like a cosine or sine as a function of time. So these are circuits where the voltage or the current vary like a sine or a cosine as a function of time. Okay, so let's say this is a graph of voltage versus time. Let's say this is voltage, let's say it's time. So the graph might look something like this, like a sine or a cosine. Okay, so circuits where the voltage or the current vary like this, like a sine or a cosine, are called AC circuits. All right, now first let me state the symbol of AC source. The symbol of AC source is this one, a circle with a symbol of sine inside. Okay, this is a symbol of AC source, a source where the voltage or the current varies like a sine or a cosine. Now, since this varies like a sine or cosine, generally AC signal can be expressed as follows. Therefore, the general expression for AC signal would be this one. Let's say it's the instantaneous voltage. You got the amplitude, and then you got sine omega t plus beta. Okay, so this is the general expression for AC voltage. So in this formula, that's how you express an AC voltage. So in this formula, this is instantaneous voltage, that is voltage at a given instant of time. So it's called the instantaneous voltage. Instantaneous voltage, that is a voltage at a given instant of time. This one is a maximum value, this one over here, okay, the capital V. This is the maximum value, and it's called the amplitude, and it's called the amplitude. And then we have this number over here, omega, that is angular frequency, and determines how fast it is oscillating back and forth. Okay, so the unit for this one is radian per second. So unit of omega is radian per second. You can say angular frequency is number of radians executed per second. So the unit of angular frequency is radian per second. Okay, because angular frequency, you can say, is number of radians executed per second. And as we have seen before, angular frequency can be related with frequency. Since there are 2 pi radians in a cycle, since there are 2 pi radians in a cycle, we can say that omega equals 2 pi times frequency. Always remember F stands for frequency or number of cycles per second. This is number of cycles per second. Okay, and if you remember, frequency is the inverse of period. Okay, T is the period or time taken for one cycle. Okay, time taken for one cycle. So we can say omega equals 2 pi f, or 2 pi divided by the period. Okay, and then we have a third property which is very important in this chapter. This number over here is called the phase angle. Beta is called the phase angle. Beta, the number beta is called the phase angle. Is called the phase angle. Phase angle. Its effect is to shift the graph either to the right or to the left. Its effect is to shift the graph to the left or to the right. For example, you can say that cosine is sine shifted by a 90 degree. You see, you've got the following sine like this. Now if you pull this to the left by 90 degree, so 90 degrees from here to here, or pi over 2, then you will get sine. If you pull this, if you shift it to the left, then you'll get the graph of cosine. So you can say that a cosine is actually sine shifted by pi over 2, or 1/4 of one cycle. So the effect of this is simply to shift a graph to the right or to the left as it is. Okay, so this will go like this. So this is sine, and this will give you cosine when you shift it by 90 degree. Okay, so this property is going to be very important in this chapter. All right, its effect is to shift the graph to the right or to the left as it is. Now let's look at phase shift. Phase shift between two signals is the difference between their phase angles. The phase shift between two signals is the difference between their phase angles. Okay, for example, let's say we have the following two signals. Let's say V1, and then we've got amplitude sine omega t plus beta 1, and then let's say the second one is amplitude V2 sine omega t plus beta 2. Okay, so the phase shift of signal 2 with respect to signal 1 is the difference beta 2 minus beta 1. Okay, so phase shift of signal 2 with respect to signal 1, if represented by theta, then we have theta equals beta 2 minus beta 1. So this is the phase shift of signal 2 with respect to signal 1. Now, if this expression is positive, we say signal 2 is leading beta 1 by this much. But if this one is negative, we say signal 2 is lagging from signal 1. Okay, so if beta 2 minus beta 1 is greater than 0, we say signal 2 is leading, let's say leading signal 1 by theta. Okay, and if it is negative, beta 2 minus beta 1 is less than 0, we say signal 2 is lagging from signal 1 by theta. Okay, or you can say signal 1 is leading if you want. All right, so phase shift between two signals is simply the difference between their phase angles. In this chapter we're going to look at the phase shift between voltage and current for different kinds of circuits. Now let's consider an example. Suppose we have the following two signals. Let's say we have y1 equals maybe 10 times sine of 10t plus pi over 2, and y2 is, let's say, maybe 20 sine 10t, let's say, minus maybe pi over 4. Okay, the question is determine the phase shift of signal 2, that's the second one, signal 2 with respect to signal 1. Okay, so we see that beta 1, this is the phase angle of signal 1, is pi over 2, and beta 2, the phase angle of signal 2, this is pi over 4, but it's negative. Okay, therefore we're looking for the phase shift equals beta 2 minus beta 1 equals negative pi over 4 minus pi over 2. Okay, so this is 2 pi over 4, so you get negative 3 pi over 4. Okay, so the phase shift between signal 1 and signal 2 is negative 3 pi over 4, and we say beta 2 is lagging from, signal 2 is lagging from signal 1 by 3 pi over 4. Okay, so in this case signal 2 is lagging. Signal 2 is lagging by 3 pi over 4, and signal 1 is leading, or you can say signal 1 is leading by 3 pi over 4. All right. Now next we're going to look at a case where AC source is connected to a resistor. Okay, AC source connected to a resistor. Okay, so we have a circuit like this. We have this AC source, and then this is connected to a resistor. Okay, this is R. Now let the voltage of the source, maybe let me already say, let the voltage of the AC source be V sine omega t. Okay, now as we know, the property of a resistor is characterized by Ohm's law. So you have a current over here, and Ohm's law says that the voltage is proportional to the current, and the constant proportionality is the resistance. Okay, so Ohm's law is also applies for instantaneous voltage, instantaneous current. So Ohm's law implies the voltage equals resistance times current. Okay, so the current, the instantaneous current, is instantaneous voltage divided by the resistance. All right, so we have this equals this instantaneous voltage is V sine omega t divided by the resistor. Okay, so it follows that this is the amplitude of the current. Okay, now we can say this equals amplitude of the current times the sine of omega t. Okay, so it follows that the amplitude of the current equals amplitude of the voltage divided by the resistance. Okay, so we have this relationship between the amplitudes. Capital I is amplitude of current, and of course capital V is amplitude of voltage or potential difference. Okay, and of course R is the resistance of the resistor. Okay, so Ohm's law also applies between the amplitudes. All right, now let's look at the phase shift. Okay, so what we have is we have V equals V sine omega t, and then we have the current equals V over R times sine omega t. Okay, so let's look at the phase shift of voltage with respect to current. Phase shift of voltage with respect to current. Okay, so when you call it theta r, that's a phase shift for resistor, that will be the phase angle of the voltage minus the phase angle of the current. Okay, now this is omega t plus 0, so the phase angle of the voltage is 0. The same thing with the current, the phase angle of the current is 0. It follows that the phase shift of voltage with respect to current for resistor is 0 minus 0 equals 0. So we have theta r is equal to 0. So there is no phase shift between voltage and current for a resistor. In other words, they are in phase. They oscillate together. So this means the phase shift of voltage with respect to current for a resistor is 0. For a resistor is 0. In other words, voltage and current are in phase. In other words, for a resistor, voltage and current are in phase. That is, they oscillate together. Okay, now if you want to look at it graphically, let's say this is the current. Let's say this is current. Now the voltage might have a different amplitude, but they're going to reach maximum and minimum together. They're going to go like this. There is no phase shift in them. They reach maximum and minimum together. That's what I mean by no phase shift. Okay, these two maximums match, or minimums. They're oscillating together, up and down. So for a resistor, the phase shift in voltage and current is 0, and also Ohm's law applies for the amplitudes. All right. Now let's look at an example. Let's say a resistor of resistance, let's say 10 ohms, is connected to an AC source that varies with time, with time according to the equation. Let's say V equals maybe, let's say 2 volts times 2 volts times, let's say, sine of let's say 60t, like this. This is how the voltage varies. So we've got an AC source whose voltage varies according to this equation, connect to a 10 ohm resistor. Okay, so let's ask some questions. A, calculate the amplitude of the current. Calculate the amplitude of the current. Okay, so we're looking for capital I, amplitude of current. All right, you know, the current is given like this. Well, let me calculate amplitude first. So the amplitude of the current is amplitude voltage divided by resistance. This is amplitude voltage, which is 2. So V equals 2 volts. So that is 2 divided by 10. That is 0.2 ohms. So, amps. 0.2 amps. So the amplitude of the current is 0.2 amps. Okay. Now, let's say determine the phase angle of the current. Determine the phase angle of the current. Okay, so we're looking for beta I. That's what we want to find, the phase angle of the current. What we know is the phase angle of the voltage is 0 according to this equation. Okay, so beta V is equal to 0, but also we know theta R, which is beta V minus beta I, is also 0. They're in phase. So this implies the phase angle of the current is also 0. Okay, so now let's say C, give an expression for the current as a function of time, as a function of time. Okay, so we want to find an expression for the current. Generally it's going like this: the amplitude times sine of omega t plus its phase angle. Okay, now omega is 60. The amplitude we already saw is 0.2, omega is 60, and we just determined the phase angle of the current is 0 because it's in phase, the voltage, and both of them should have the same phase angle. Therefore, it follows that the current is 0.2 sine of 60t. Okay, so this is how the current varies as a function of time. They are in phase. All right, next we're going to look at an inductor connected to an AC source. Maybe let's start with the capacitor. A capacitor connected to an AC source. Okay, so in this case we have an AC source connect to a capacitor. Okay, now a capacitor is identified by its capacitance C, and let's say the voltage, the AC voltage varies with time according to the following equation: V sine omega t. Okay, so a capacitor is characterized by the following equation: charge equals capacitance times potential difference, right? That's how a capacitor is characterized. The charge accumulated by a capacitor equals its capacitance times the potential difference across the capacitor. Okay. Now, as you know, current is rate of change of charge. Now I cannot do this without using calculus, so I'm going to use calculus. So rate of charge with respect to time in calculus is the derivative of charge with respect to time. Okay, so the current is the derivative of charge with respect to time. Okay, and that is C times the derivative of voltage with respect to time, because voltage is a constant. Okay, and so we just assume that the voltage is varying like a sine function like this. So we have the following: the instantaneous current is capacitance times the derivative of the instantaneous voltage, which is V sine omega t. Okay, and for those of you familiar with calculus, the derivative of sine is cosine, and from chain rule we'll get angular frequency out. So this is capacitance times angular speed times V, and then you've got cosine omega t. Okay, so the current is given, the instantaneous current is given by this equation. Now, for the sake of comparison, when we look at the phase shift, we will write this in terms of a sine function. Okay, now let's expand this one. Sine omega t plus pi over 2. Using the formula for expanding the sign of sums, this is sine omega t times cosine pi over 2 plus cosine omega t times sine pi over 2. Okay, so cosine pi over 2 is 0, this goes away. Sine pi over 2 is 1, so we have the following formula: cosine omega t equals the sine of omega t plus pi over 2. Okay, so using sine omega t plus pi over 2, we can write this as current, or instantaneous current, equals capacitance times angular frequency times amplitude voltage times the sine of omega t plus pi over 2. Okay, and of course we've seen that V is V sine omega t. All right, so what this tells us that the amplitude of the current I is C omega times V. Okay, so this is the amplitude of the current. Amplitude of the current. Now we're going to define a quantity called capacitive reactance, which is basically the resistance of a capacitor. So let's define what a capacitive reactance is. Capacitive reactance, we're going to use XC to represent it. Capacitive reactance is defined to be the ratio between the voltage and the current across a capacitor. This is defined to be ratio of voltage across a capacitor to the current through the capacitor. Through the capacitor. Okay, so this is the definition of XC, or capacitive reactance, is the voltage through the across the capacitor divided by the current through the capacitor. All right, now this is the amplitude of voltage, so we're using V for that. So we're using BC, in this case is V, and the IC we just saw is, well, let me put that in a box first. Okay, and this is voltage divided by current, so unit of XC is ohms. Unit of XC is ohms, is voltage divided by current. Okay, it's ohm or omega. All right, now so in our case over here, the amplitude of the voltage across the capacitor is this, capital V. So you've got the voltage across the capacitor in our case is capital V, and the current through the capacitor we just obtained over here is capacitance times angular speed times velocity. So you've got capacitance times angular frequency, and then times the amplitude of the voltage. Okay, so it follows that the capacitive reactance for a capacitor is V divided by C omega V, which is 1 over capacitance times angular frequency. So you see the capacitive reactance of a capacitor is inversely proportional to the frequency. Okay, or you can say, or since omega is 2 pi f, you can also say xc equals 1 over 2 pi f c. Okay, so this is basically the resistance of a capacitor. So the reactance for capacitor is inversely proportional to the frequency. So reactance of a capacitor is inversely proportional to the frequency of the signal, that is, the greater the frequency, the smaller the reactance or the resistance. Okay, signal. Okay, so the resistance of a resistor is a constant, but for a capacitor the resistance or the reactance depends on the frequency. The greater the frequency, the smaller the capacitive reactance. Okay, now let's look at the phase shift. Phase shift of voltage with respect to current. Let's look at phase shift of voltage with respect to current. With respect to current, we're going to use theta c. Okay, so we have theta c equals the phase angle of the voltage minus the phase angle of the current. Okay, but we have the expressions over here. So for the current, the phase angle is pi over 2. For the voltage, the phase angle is 0. You see that? So we have beta V equals 0, beta I equals pi over 2. Okay, so the phase shift of voltage with respect to current is 0 minus pi over 2, or theta c equals negative pi over 2. All right, so the phase shift is negative and is pi over 2 or 90 degree. Okay, so what does this mean? In a capacitor, you see the voltage lags from the current by 90 degree or pi over 2. So this implies in a capacitor the voltage lags from the current by pi over 2 or pi over 2 radians or 90 degree. Okay, that is the conclusion. So the current leads the voltage by pi over 2. So if this is a current, let's say this is the voltage. Let's say this is V. Then the current will start at maximum. Okay, it leads this will go something like this. Okay, and this would be the current. That is, the current leads the voltage by 90 degree. You see this difference over here? It's 90 degree or a quarter of a complete cycle. All right. in other words, this is, if this is sine omega t, the current is sine omega t plus pi over 2. Okay, that means the current leads the voltage by 90 degree. So in a capacitor, the voltage lags from the current by pi over 2. Or you can say the current leads the voltage, or the current leads the voltage by pi over 2. That was the same, by pi over 2. Okay, so the important conclusions over here are the capacitive reactance, which is basically the resistance of a capacitor, is inversely proportional to the frequency of the signal, and the current leads the voltage by pi over 2, or the voltage lags from the current by pi over 2. All right, let's look at an example. Let's say a capacitor of capacitance, let's say 2 farad, is connected to an AC signal or alternating current that varies with time, let's say according to the equation. Let's say the instantaneous voltage is given like this, maybe 10 volts times sine of, let's say, maybe 20. Okay, that's the voltage. All right, so let's ask some questions. A, calculate the capacitive reactance of the capacitor. Capacitive reactance of the capacitor. Okay, so we're looking for XC, question mark, and we saw that XC is 1 over angular frequency times capacitance. Okay, so this is the angular frequency, omega, that's 20 radian per second, and the capacitance we're told is 2 farad. Okay, so the capacitive reactance is 1 over 20 times 2, or 1 over 40 ohms. Okay, so the capacitance of the reactance or capacitive reactance, which is basically the resistance of the capacitor, is 1 over 40 ohms. Okay, now let's say determine the amplitude of the current. The amplitude of the current. Okay, so the amplitude is the voltage across the capacitor divided by the capacitive reactance, right? Now the voltage is 10, and we just calculated the capacitive reactance to be 1 over 40. Okay, so the current is very big, doesn't make sense, but anyway, so 10 divided by 1 over 40 would be 400 amp. It's not realistic, but using the numbers we use it, that's the answer. All right, 400 amps. All right, and so C, determine the phase angle of the current. Determine the phase angle of the current. Okay, so we're looking for the phase angle of the current, question mark. What do we know? Theta C, which is beta V minus beta I, is negative pi over 2, right? but the phase angle of the voltage is 0. You see, this is plus 0, so the phase angle of the voltage is 0 and beta V is 0. So it follows that 0 minus beta I equals negative pi over 2. So the phase angle of the current is pi over 2. Okay, now we have the amplitude, we have the frequency, we have the phase angle. Now we can write an expression for the current as a function of time. Okay, so D, and this really give an expression for the current as a function of time, as a function of time. Okay, so the general expression is this one, the amplitude of the current, and then you've got sine omega t plus its phase angle beta I, right? But we just calculated the amplitude is 400 amps. The angular frequency is 20, remember this one over here, 20, and the phase angle of the current we just calculate to be pi over 2. So the current is given by the amplitude 400 sine of 20t plus pi over 2. Okay, all right, now we're going to look an inductor connect to an AC source. An inductor connected to an AC source. Okay, so we have a source connected to an inductor, which is a coil. Okay, and as you know, an inductor is characterized by its inductance L. Okay, now we're going to assume the current I varies with time according to the following formula: I sine omega t. Okay, now if you remember, the voltage, the self-induced EMF of an inductor is proportional to the rate of change of current. All right, so you've got well, if you apply Kirchhoff's law to this one, you say V, this voltage over here, and then you've got the voltage across the inductor is negative L. Well, let's delta I by delta T, like this, equals 0. That's applying the loop rule of Kirchhoff's loop rule. So we have the voltage is equal to inductance times rate of change of current with respect to time. Okay, this is the voltage across the inductor, this is the source V. All right, now I cannot do this without using calculus, so I'm going to use derivative for this one. Okay, we're going to let delta T go to 0, and then we have the following relationship: the voltage equals inductance times rate of change of current with respect to time. Okay, for those of you familiar with calculus, this delta T approaches 0, this basically becomes the slope of the tangent line, or of the graph of current versus time, or the derivative. But don't worry about it, but I need to use it to do this. Okay, so we have said that let I be I sine omega t, so we have the voltage is L, the derivative of the amplitude of the current times sine omega t. Okay, and that derivative is L amplitude current times angular frequency times cosine of omega t. Okay, but as we've seen earlier, cosine, let's say cosine omega t is the sine of omega t plus pi over 2. Okay, so with that I have, if I equals I sine omega t, then the voltage is Li times angular frequency sine omega t plus pi over 2. Okay? Now, first, let me look at the inductive reactance. Let's define the inductive reactance, which is basically the resistance of an inductor. Okay, we're going to use XL. Okay, this is defined to be ratio of voltage across the inductor to the current through the conductor. This is defined to be ratio of voltage across the inductor to current through the inductor. Okay, the current through the inductor. Okay, so this is defined to be the amplitude of the voltage across the inductor divided by the current across the inductor. All right, so what do we have? The amplitude of the current is I, so you've got IL equals I. Let me put that in a box over here. The reactance is the ratio between the voltage and the current. So look, the amplitude of the current in this equation is I, and the amplitude of the voltage, you see, is inductance times current times angular frequency. So it follows that XL, or inductive reactance, is inductance times current times angular frequency divided by the current, or L times omega. So you've got the following formula. The inductive reactance is inductance times angular frequency, or since omega equals 2 pi f, also equals 2 pi f times L. Okay, so it follows that the inductive reactance of an inductor is proportional to the frequency. It's not a constant. If you double the frequency, the resistance will double. If you triple, it will triple, and so on. So as you can see from here, the inductive reactance of an inductor is proportional to the frequency. The inductive reactance of an inductor is proportional to the frequency of the signal. Proportional to the frequency of the signal. Okay, so for a capacitor, the reactance is inversely proportional to frequency, but for inductor, the reactance is proportional to frequency. Now we're going to look at phase shift of voltage with respect to current. Phase shift of voltage with respect to current for inductor, with respect to current. All right, we're going to use theta L. So theta L is the phase angle of the voltage minus the phase angle of the current. Now if you look at these two equations over here, you see the phase angle of the current is 0. So you've got beta I equals 0. And if you look over here, the phase angle of the voltage is pi over 2. So beta V equals pi over 2. All right, so it follows that theta L equals pi over 2 minus 0 equals pi over 2. Okay, so we have the following result for an inductor. So for an inductor, the voltage leads the current by pi over 2. So for an inductor, the voltage leads the current by pi over 2 radians, or 90 degrees. Okay, or you can say the current lags from the voltage by 90 degrees, or the current lags from the voltage by pi over 2. Okay, so let's say this is the current like this. That's like a sine. Let's say this is the current. Then the voltage would be at this point, you see, we'll say 0 plus pi over 2, which is 1 over here. So the voltage will go like this. Will go like this. That's the V. And so on. Okay, it leads by pi over 2. All right. So the main conclusions for inductor are: for inductor, the voltage leads the current by 90 degrees, and also the inductive reactance is directly proportional to frequency. The greater the frequency, the greater the resistance. All right. Now let's look at an example. Let's say an inductor of inductance, let's say 2 Henry, is connected to AC source that varies with time according to the equation. Let's say V equals maybe 10 volts times the sine of 10t. Okay. A, calculate it is inductive reactance. Inductive reactance. So looking for XL. Okay. But we know that XL is 1. No, it's omega times L. Okay. XL equals omega times L. Omega times L. So what do we know? This is omega. Omega equals 10 radians per second. And the inductance we're told is 2 Henry. This is 2 Henry. All right. So the inductive reactance is 10 times 2, or 20 ohm. Okay. This is the inductive reactance of the capacitor. B, calculate the amplitude of the current. The amplitude of the current. Okay, so the definition of XL is V divided by amplitude voltage divided by amplitude of current. So the current is amplitude of the voltage divided by the inductive reactance. Okay, so the amplitude of the voltage is this one over here. So we've got V equals 10, and we just calculate XL. So this one is 10 divided by 20, or 0.5 amps. 0.5 amps. Okay. Okay. Now let's calculate the phase angle of the current. C, calculate the phase angle of the current. The phase angle of the current. Okay, that is, we're looking for beta I question mark. What do you know? The phase shift of voltage with respect to current for the case of inductor is the phase angle of the voltage minus the phase angle of the current, and that equals pi over 2. Right? Now the phase angle of the voltage, according to our assumption, is 0, right? We started by the phase angle of the current is 0. You see, the phase angle of the current is, well, we already know it's 0, so But well, in this case, we start from the voltage being 0, okay? So we know the phase angle of the voltage is 0. Okay, this is a problem for this problem. The phase angle of the voltage is 0, so we have to calculate beta I. So what we have is phase angle of the voltage 0 minus the phase angle of the current equals pi over 2. Okay, so it follows that the phase angle of the current is negative pi over 2. Okay, now give an expression for the current as a function of time. For the current as a function of time. Okay, so the general expression is this one: amplitude times the sine of omega t plus the phase angle. Okay, that's the general expression. And we just calculated all these quantities. So the amplitude is, you see, we just calculate over here. It is 0.5 amps. This is 0.5 amps. The frequency is the frequency of the signal, which is 10. You see that's the frequency is 10. So that's 10 radians per second. Radians per second. How about the phase angle? We just calculated. It is negative pi over 2. So it follows that the expression for the current as a function of time is 0.5 amps times the sine of 10t minus pi over 2. Okay, so this is the expression for the current as a function of time.